已解锁，请启充话筒。
圆形变形了。 Hey, good morning to everyone. Then we 3 hour lecture. Hopefully we can survive this first week. Um, right. So there are some admin stuff I still want to update you, and also project one. Do you guys want to start lecture first, then we brief on the second hour, or do you want to brief now? What do you think? Huh? What do you think? Second hour when is it all of you come up? Why not? Okay, maybe I brief in the second hour. When you get bored to study, then we do something else. Okay, so let's continue from last lecture first. So let's recall where did we left last lecture. Okay, so there's really one definition I taught on Wednesday. Anyone recall the definition? Once bunch of number, right? Bunch of number, a list of number. What sort of number I can take? Remember what number we can take? Yeah, real numbers. Okay, we can take any real numbers. Is it just random number? Put bunch like that? No. So I need to do it in a definite order. Okay, I need to order them. Remember A1, A2, A3, A4, I need to order them. Okay. So naturally there's an order of natural number. How do you order natural number? Based on how large they are. So 2 is greater than 1. 3 is greater than 2, greater than 1. Okay, so 3 comes after 1 and 2. Right or not? Okay. And last time I gave an example, right? Last time I gave an example of sequence. So what sort of sequence I gave last time? 1, 4, 7, 10, 13, 16. Okay, so can you guess what number comes next? 19. Warm up, warm up. This is a warm up. 19. Is it 19? Everyone agree? Okay, so I mean, how do you come up of 19 actually? Okay, what's your thought process? Okay, what's your thought process? Ilian, what's your thought process? Why you guess it's 19? Sorry? Yay, good. Subsequently, addition of 3 subsequently. So meaning what? You add 3 to 1. You add 3 to 4. You add 3 to 7. So this is what? This is, how do we describe this? This is what we call the recursive formula. Right. You start with 1. Okay, and then what's the next one? You take the previous one and add 3. So this is the recursive formula. So this is your thought of thinking. Does it make sense? Make sense or not? Okay. So for n greater or equals to 2, and these n live in natural number. Okay, does it make sense? Okay. But I don't agree on. This is not how my brain works. This is not how my brain works. How my brain works is this way. I recognize that all these numbers follow a pattern, a shape, if I want to put it another way. Follow another shape. What shape is it? I can look at the formula an equals to 3n minus 2 for all n in n. Is it true? Let's check. So let's do some sanity check here. What is 3 times 1 minus 2? What is 3 times 2 minus 2? What is 3 times 3 minus 2? And so on. Right. Okay. And what can you see? So you can see that first one you get 1. Second, you get 2. And then the third, second you get 6 minus 2, 4. Then third one you get 7, and so on. Okay. Does it make sense? So these two formulas represent two kinds of thinking, but both of them are the same. So my claim is, okay, what is my claim here? So here's my claim. Formula 1 equals to formula 2. Okay, so then define the same sequence. So how do I prove it? Can you prove it? How should I prove this statement here? How should I prove this statement? So I claim that they are the same. So how should I prove it? So if you want to prove this equal, right? Okay. So I mean, to be precise, maybe I put if and only if to be clearer for what we need to do next. Formula 1 if and only if formula 2 is true. Okay. So if and only if, how to prove? So there are two directions. So suppose formula 1 is true, you want to show that formula 2 agree with formula 1. Okay. So let's put it more precise. Formula 1 and formula 2. So let's do it. So let's do one way. Let's suppose we have AN. Sorry, let's put it this way. A1, maybe do it this way. AN is defined by 1. So equals to 1 when n equals to 1. And then AN minus 1 plus 3 when n is equals to, or n is greater or equal to 2. Okay. And the other one we have Bn. Let's call it Bn so that we don't confuse ourselves. There are two different sequences here. So Bn is defined by let's see, how should we put this? So maybe we remove this is better. It's because we are defining in terms. So Bn is equals to 3n plus 2 or 4n. Okay, let's give us two sequences here. Okay, so I define sequence using the n of terms. Okay, the n term is what? Okay. So what do you want to show first? Okay, so let's see where we can start here. Any idea? You know where to start? How to prove this? How to show that these two are equal? So this is equal as what? Equal as what? Remember last time we talked about different equal, equal as number, equal in modular arithmetic, equal in different number system. But here, when I want to show they agree, they are equal as what? Function, yeah, you can say they are function, but more precisely is sequence, right? They are sequence, but later we'll talk about sequence as a function, okay? So we have to show that they are equal as sequence. So how do you show two sequences are the same? So sequence is made up by what? Again, go back to definition again. What is the definition of sequence? I repeat, list of number, right? Not just list of number. What else is important? In a definite order. They are in order one. Or not just number. For example, 112 and 121 is different order already. Although they have the same number. Okay. So meaning what? You need to check that A1 equals to B1, A2 equals to B2, A3 equals to B3, A4 equals to B4, and so on. And you need to check for infinitely many times, right? Because our sequence is infinite. So what tool you can use to do this? Sorry? Yes, induction. Okay, because these are defined using natural number. Okay, you need to show for all natural numbers. The tool you use is induction. Okay. So a very good exercise is write down what you want to show for every proof. Okay. We want to show that AN equals to BN for all n in n. So you want to show it true for all n. So you need to use induction. Okay. So how do you start with induction? 3-step, right? Induction. So first you need to do base case. So what's the base case here? N equals to 1. Good. So when n equals to 1, what is AN? A1. What is A1? 1. Good. B1 equals to 1. Before that, what do you get? You need to prove me why B1 is 1, right? AN is 1 is why? By construction. No need to compute 1. I already defined for you. But Bn is different. It changes with n. Correct or not? So B1 equals to 3 times 1 minus 2, which is 3 minus 2, which is 1. Okay. So A1 equals to B1. Okay. Does it make sense? Okay. So we prove the base case. Okay. So we assume that inductive hypothesis. So assume AN equals to BN for n equals to k. Let's say it is true for some k. Okay. Then what do you need to do next? Inductive step. We want to prove that AK plus 1 equals to BK plus 1. Okay. Assuming it's true for some number, I want to show that it is true for the next number. Okay. So should we start with BK plus 1 or AK plus 1 first? What do you think? Let you pick. Where should we start? You want to start AK plus 1 or BK plus 1 first? BK plus 1, okay. You can start with AK plus 1 as well. We can, but let's start with BK plus 1 first. So consider BK plus 1. Okay, what's the formula for BK plus 1? Remember, still remember? Let's recall for you. So if you replace n by 3k plus 1, you get what? Yeah. 3 times k plus 1 minus 2. Okay. So all together here, what do you get? 3k plus 1 minus 2. Okay. So should I combine them or not? Yeah. Oh, plus 3 here. Okay, thank you. Good. Plus 3 here. Okay, good. So you see, from here, what's your idea? How should you proceed here? How should we proceed? Any idea? Do you have any idea? Okay, you need to somehow use the assumption, the inductive hypothesis. But remember, what's your goal? You still remember your goal or not? What's your goal? You need to get to the final AK plus 1 here. Okay. But what is AK plus 1? Maybe you can work backward now. Try and work backward. So what is AK plus 1 here? What's the definition of AK plus 1? Because we already proved for n equals to 1, right? For sure, all these k should be greater or equal to 2. Okay, so we can use the formula for n greater or equals to 2. Okay, so I should get a k plus 1, the previous one, term plus 3. Right, this is how Yuliang told you, right? I just add 3 to the previous one. Right? I just add 3 to the previous one. Okay, but what is this? This is just AK plus 3. Yay! I see AK now. I see AK already. When I see AK means what? I can apply inductive step. Correct or not? Because I know that AK equals to BK for n equals to K. So this step here I will write by inductive hypothesis. Okay. How about the rest? This one is just by definition. Okay, since K is greater or equals to sorry, the last one is by definition. By definition, since K is greater or equal to 2. The middle one is just calculation. Okay, but can we connect here or not? Are we allowed to connect here? Connect here? Is it clear? Is it obvious? 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 Why? Because it is just BK. How should I put this? Wait. Thank you. So what is the definition of BK? BK is simply 3K minus 2. So meaning what? Meaning we just put minus 2 beside 3K, we will get BK. Okay. So here is also by what? By definition of BN. Okay. And then the top here is what? This one maybe not so important for you, but in MA will be quite precise in here. We will call this by commutativity. Okay. You can commute plus 3 and minus 2. Does it make sense? Okay or not? Okay. So when you want to show something is equal, so the moral here, when you want to show something is equal, typically you can start from one side first and then go to the other side. Go from BK plus 1 equal to the end, AK plus 1. Okay. Or you can start with AK plus 1 equal to BK plus 1. Okay, you can do both ways. It's fine. But as long as you add in this justification. Okay, don't hand in me assignment like this equal. I don't know why equal. You just equal. Okay, so make sure you write down by definition or by assumption. Okay, or by definition. Does it make sense? Okay. Okay. Make sense? Any question? Please ask a question. Don't be shy to ask. Oh, yeah. Yes. Yes, that's right. Yes. Yeah. Everyone heard what she said. Everything right in blue pen is what you need to write in your assignment. Correct. The one I wrote in this purple thing is more advanced, not so important in your class here, but I want to give you an idea what I am doing. Okay. Actually, I commuting -2 and +3. Commute. So, okay, so this is actually what I want to tell you is it's not natural. Okay? It's not natural in higher mathematics. Although in your high school, you simply swap, right? B times A equals to B times A equals to A times B. A plus B equals to B plus A. So these are not natural actually. Okay, but this is how you train in your high school. Okay, yeah. So, so are we done yet? Yeah, so we are done. So by induction, an equals to bn for all n in. Okay, a side question. Do you know why this inductive proof is designed in this 3-step here? Do you know why? Do you know why once you prove these 3-step, it is done for infinite terms? You know why? No, there's no somehow in mathematics. Mathematics must be precise. Every question have an answer. We must get an answer. Okay. So anyone know why? Maybe not very precise when you explain to me. Just an idea first. Anyone want to try? Why? Why 3-step can show for A100, A1,000,000? Sorry? What is the model exponent you use? Alright, explain more.
Testing the inductive hypothesis and the extents patients.
So
And the basis case is
let's say if I prove this, how do I imply A1,000,000 equals to B1,000,000? How? How? I only show you A1 equals to B1. How about A1,000,000? How? Right? Explain more. Elaborate.
Step to prove A2 equals to B2 and so on, so on.
That's right. That's right. So if you want to show that A1,000,000 equals to B1,000,000, you need to have A 999999999. I don't know how many nine you can count it. Equals to B 9999999. Right. But for A 9999 and B 999 to be true, need to be true for A 998, for example, equal to B 998. And then you can go all the way back to A2 equals to B2 and then A1 equals to B1. But I have shown that A1 is equal to B1. So I can reduce all the numbers. Because this K here is arbitrary. Okay, no? So the main key here, this K is arbitrary. Does it make sense? Any question? No question. Arbitrary and this K. Arbitrary and greater or equals to 2. No question? No? Okay. In particular, another way to put it is from A1 equals to B1, we can deduce A2 equals to B2. How? Because by hypothesis, this inductive hypothesis would imply that AK plus 1 equals to BK plus 1. But we prove that A1 equals to B1, so A1 plus 1 equals to B1 plus 1, which is A2 equals to B. And then so on and so forth. Okay? Yeah. So inductive proof is a very important tool in mathematics because you can show for infinite terms. Okay, infinite terms. Okay, natural number, many of them. Okay, so whenever you want to show something is true for infinite terms, you need to use inductive step. I mean, for infinitely many natural numbers. Okay, any question? before we proceed? Okay, if not, let's continue. All right, so now I want you to try and work out this. So try and find the first, second, and third, fourth term of the following sequence. Let's give you 3 exercises. Let you spend some time doing them. So first exercise is to figure out the first 4 terms of the sequence. So you need to familiarize yourself with different way of expressing these sequence. Second, let's find formula. Following sequence. Okay, let's do 2 of these first. Okay, I give you, is it 3 minutes enough or not? If you 3 minutes to do this, you can talk with your friends, discuss with your friend. Okay, ask the friend beside you. Okay, introduce yourself to them. You can discuss. And try and do this exercise now. Then try talk with your friends. Check, do you guys have the same answer? Because this is exactly how I want you to work with your assignment. And discuss idea with your friend. Make sure you make some friends to discuss. Your friend. Then check whether you guys have the same answer. Different working is very good. Different mind, different people have different mind. Okay, is everyone almost done? Okay, let's discuss. By the way, if you feel too fast, please slow me down. You can slow me down by asking questions. Okay. Otherwise, if you miss something, this thing will gonna accumulate a lot. Okay, you'll lose forever. So let's start with A. What is A1? What's A1? Like too slow already. This calculation. Huh? 0. So why is it 0? 1 minus 1 over 1. Okay, which is 1 minus 1 equal to 0. So make sure you write down the statement. Don't simply write 1 equals 0. Everyone is 1 equal to 0. But how do I know you know? So you need to prove me that you know. So everything how you want to ask me how to write my answer. Very simple question you need to answer. Demonstrate that I can know that you know. Okay? That I can check that you know. You can prove to me that you know. Okay? This is how you have to present your solution. Okay? Prove to me that you know. Okay? A2. What is A2? What's A2? 1 minus half, which is half. Okay. A3? Right? 1 minus 1 over 3, so you get 2 over 3. So I'm being lazy here. A4? 3 over 4. Okay, make sure you know how to get all of them. How about Bn? B1. B1 is 1 plus minus 1 to the 1 times 1 over 1, which is 0. B2? 3 over 2. B3? 2 over 3. B4? 5 over 4. Okay, good. Okay, so C don't have a name. So let's give it a name. Let's call it C. Okay. Hey, by the way, did you guys notice sometimes I put dot dot equals, sometimes I put dot dot. You know what's the difference or not? What's the difference? What's the difference? Which one is definition? Okay, dot dot equal is the definition. Okay, equal sometimes you have to justify why they are equal. But definition you cannot justify. I just define it. It is like that. Nothing to show. But sometimes when we write down equal, you need to prove. Okay, why is it equal? Okay, good. So what is C1 here? Oh, not C1. Oh. Where do I start from? Anyone's compute C1? Where do I start this sequence here? Huh? N equals to 3. Okay, so actually the first term here is C3. Okay. So what is C3 here? What's C3? Minus 1 to the 3 plus 1 over 3. So what is it? It is 2 over 3. Good. So what's the next term? C? 4, which is 5 over 4. C5? 84 over 5. C6? Oh, 6. Okay, last one. 0.999 bracket. What does this mean? Only one number inside it. Repeat itself. So meaning this sequence is a constant sequence. Okay, it's constant. Every term is the same number. Okay, so meaning the first term, second term, third term are just 0.999, 0.999, 0.999, 0.999, 0.999. Okay, so this is what we call a constant sequence. Okay. So this kind of constant things is very important. Like what I said yesterday, right? Constant, not yesterday, last time. Constant function. Okay, so this is a constant sequence. Okay, so far so good. Okay, can follow. Okay. All right. Next, how about this? Find a formula for the following sequence. So like what Jiantong is it? Are you Jiantong? Yeah, like what Jiantong say, we want to see sequence as a function, right? I want to say that A1 is this term, right? A2 is this term. A1, A2, A3, A4, A5, and so on. Okay, so we want to figure out a function, okay, AN, from N to R. Okay, so how do I send 1 to 3 over 5? How do I send 2 to 3 minus 4 over 25, and so on? Okay, in a meaningful way. Okay, in a meaningful way. Okay, can we do it in a meaningful way or not? Did you see any pattern? Did you recognize any pattern? Any pattern? There are few patterns inside here, right? How many patterns inside here? 3 at least. Okay, so what are the 3? What are the 3? Hello? Hey, you cannot say 3 and then I don't know. Then this one is the talent, no? You said 3, you must tell me which 3, right? So which 3? Okay, so you have a alternating minus sign. What else? You got 2 more, right? What's the other 2? Sorry? Okay, you notice that the denominator is the power of 5. Is it true? 5, 25, 125, or 5 to the power 3, 625 is 5 to the power 4. Okay. What else? One more. 3 by 6. So you have a difference by 1 in the numerator. So how do you put all these patterns together? Can you think of a way to put this pattern together? Let's start with alternating sign. How do you make alternating sign? I think we have an example just now, right? Okay, how do we make alternating sign? Minus 1 to the n. Okay. Does n work? Plus 1 or minus 1? Sure, that's plus 1. Okay, so that when we put 1, I get 2, so I get positive 1 and then 3 negative, 4 positive. All right. How about the rest? How do you control denominator? Power of 5. So 5 to the power n. Does it work? 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 4, so on. Numerator? N plus 2. N plus 2 works. So 1 plus 2, 3, 2 plus 2, 4, 3 plus 2, 5, and so on. So this have to work for all natural numbers. Okay. So actually you put 3 patterns into 1 pattern only. Actually there's 1 pattern. Okay? 1 complicated pattern. Does it make sense? Okay. Okay. Yeah. Because I define it. Yeah, because I define it. If you want to put equal, meaning that meaning what? Meaning you define an as this, and then you give a formula for your an. If you want to put equal, also can. Yeah, just different way of expressing your answer, because this in your level still okay, but when you go to pure, it's very different. You need to prove why they are equal. Yeah, but at this level still okay, because we also are not precise not precise in writing that, listing down the number. So how do I show equal? How do I produce the infinite one? Actually, in this case, I really just ask you to find, not proof. It's like I ask you to guess. So yeah, so what time is it? So okay, so since we discussed up to this point, maybe we divert a bit, talk about what's the tone of this course here. Maybe later we can take a break. So the tone of this course, right? We actually is a bridge between arithmetic and mathematics. So like last time, what I told you, okay, so this is a bridge. You are not fully in proving yet, but you will see more proving. Okay, this will make different with your high school maths. Second, okay, the most important thing in this class is you learn a lot of maths 2. Okay, so this maths 2, right, will be useful for proving later, which is MA1 and MA2. These are the two major core course you need to take in your second year. Okay, so you learn the math tools first. In this class, you learn how to calculate. Okay, in the future class, you learn how to prove. Because when you prove, you need to know how to calculate. Remember last time what I said? Arithmetic is a subset of mathematics. Okay, so having said that, so we don't have much time to do rigorous stuff. So this course is actually not rigorous. But I offer a solution to it. So to solve this, that's why I designed this course to have two projects here. So project 1 will be the one that filling the rigorous gap. Okay, so I will talk a bit about what you can do in project 1. You can start thinking now. Okay, you don't need to do first, but you can start to think about idea what you can do in project 1. Okay, so to fill this gap, what do you need to do? So what is actually project 1 doing here? So you can get some idea from the lecture. Okay, for example, sometime maybe I told you that we won't prove it, or we need more rigorous thing, then that will become your project. You can introduce these rigorous definition and then prove some theorem inside your project. Okay, you choose some theorem or proposition to prove if we don't do it in class. Okay, if we don't do it in class. Or it might become from your own readings. I give you a lot of textbook, right? Okay, maybe some section I didn't further I didn't further pursue them, but you can do in your project. Okay, of course, this project need to be related to our topics. Don't pick number theory topics and do it here. Okay, so related to our topics, I already list down all the topics there. Okay, so for example, like soon you will see something called a monotonic sequence theorem. Okay, soon you will see this. We won't prove this, then you can prove. So what do you need to prove? For example, this statement is every bounded monotonic sequence is convergent. Okay. Yeah. So maybe you don't know all these words yet. It's fine. I just want to give you an idea. Okay. So what do you need to do in this project here? So how do you fill in the rigorous gap? So first of all, if you fix a topic, I want you to go and look for the history or the background. So who is the first guy to think about this statement, and then why they think about this statement, how they come across this statement. Okay. Often they're coming to this statement from different perspective, not calculus, maybe other perspective. Okay, so it's very interesting to find this out. Okay, actually, I see this part as a quite important section in your paper or in your project. Okay, and then next, you will put your theory in. So you need to set up your theory. So how do you set it up? You need the definitions or some statement that you need to prove your theorem also. Okay. So in this case here, for example, in this case, how many works here? 1, 2, 3. These 3 words, maybe 4 works. 4 works here. You need to introduce to me what is sequence. what is monotonic sequence, what is bounded sequence, and then what is convergent sequence. You need to introduce all words first and then prove. Okay. Next, you need to show examples. You need to give example how your theory works. In what? In maths. Okay, in maths. For example, in what kind of maths question you need this theory. Okay, so you need to show me how to apply it. Okay, how to apply. Okay, in mathematics. So lastly, in your reference, in your paper, you need the reference. Okay, you need to reference this. So references don't come from website. Although you can search for website, but try to cite some journals or books, textbooks. Okay, journal could be something from archive. Okay, so you should know about archive. How to spell archive? Archive.com. Okay, or most of the maths journal is in archive. Okay. Yeah. So you can use website for your, in real life, you can go for like Wikipedia search to learn about it. But when you cite, make sure you get a reference from journals and books. Because even Wikipedia also cite journals or books. Okay, so you can look at the reference of the website. Does it make sense? So no referencing on website in your paper. So what I want to train you here is actually this is like a mini FYP. The mini FYP. So how mini is it? So the content, what you need to do is about at least 1.5 pages. Okay, at most just go to 3 pages is enough. Okay, no need too long, short one. Okay, so 1.5 pages is what kind of concept? You see, already got 3 sections here. It's about half pages each section. Okay, not counting reference. Not counting reference. Just these 3 sections have to make out 1.5 to 3 pages. Okay, not need too long, but I want you to spend time research. Okay, so this thing need to be outside the lecture notes, not taught by me, man. Okay, better. And if not, maybe you get less mark. If you are really weak, maybe I can give exception, but try to get something that I don't taught in this. Any question? Related to MA1, don't go to other field. Then related to MA1. I list down the topics, right? You can go and read the textbook in advance if you like. But this deadline is quite long, I guess, until week 10, I think, if not wrong. So you have like 10 weeks to go through with me most of the content. Then along the way, you can see which topics you like, suit you. Okay? Make sure you come and discuss with me before you decide your topic. Okay, discuss with me first. I approve, then you continue. Does it make sense? Okay. So far, any question about this project? Okay, you can start thinking about what topics you want to do. And then along the way, I can tell you, oh, you can try and do this in your project, try to do this in your project. And you can consider different options. Okay. So you can also, one very original thing you can do is think out of one question by your own and then prove it. Maybe you come out with a lemma and then you prove it. Come out with a proposition, you prove it. Maybe there's some property of sequence you want to prove it. Okay. Time 9:50, very good timing. Okay. So any question before we take a break first? Any question? Any idea? When times come, we will review more detail. But detail is in your course information also. Okay, so have a read. Okay, 9:50. Let's break until 10. Everyone. Not everyone is calculus 2 last time. Related to calculus 2. I don't do calculus 1, calculus 2. Okay.
给我的这边。
啊，
的角度。
哦，对着你啊。灯痊愈，健康，永离，小恩，精神，痊愈，哎，痊愈，痊愈啊，你是痊愈啊？OK，止盈，雄，天气，一轩，公平，春夏，力量，危气，晦气嘛，还是晦气？OK，晦气，开轮，异象，异象，回旋，安波，安波，哦，OK，小鹰，小羊，，OK，一平，袁一平，袁一平啊，要袁一平，OK，小羊 not here，OK，not here，一平 are you in the team group chat yet? Not yet. Can you look for yeah, Chen Yu? Yeah. Let her add you in. Alright, let's start. Right, so first question here. So can you find a recursive formula for this Fibonacci sequence here? Give you 1 minute. Can discuss with your friend. Give a recursive formula for this Fibonacci sequence. Try to discuss with your friend. Yeah, talk to the person beside you. Yeah. Okay. Any idea? Any idea how to define a recursive formula? So you need to start with base case, right? Okay, what's the base case? A1 equals to 1. And then what's the rest? Sorry? Yeah. Need to add two base case. Okay, seems like we need two base case. Why? Why? Mm-hmm. So when you look at this pattern, how do you observe this pattern? How do you observe this pattern? First is 1. Second is 1. 1, 1. Could it be 1, 1, 1, 1, 1, 1, 1, 1, 1? Hey, no way. 1, 1, 2. How does 2 come from? Maybe 1 plus 1 equals to 2. But let's see what's next. It's 3. Could it be 1 plus 1 plus 1 plus 2? Because you add the previous 2. Can we add all of them together? No way, it's 4. But I want 3 only. So how? Maybe just the previous 2 will work. Right? 2 plus 1. Again, let's guess again. 5. Next one is 5. Previous 2, 2 and 3. Add together 5. Seems like working, huh? 8. Also 5 plus 3. And so on and so forth. Okay, so we can see that if we set two base case here, and then we set an equals to the addition of previous two terms, we'll get the Fibonacci sequence. Okay. So this question asks you about recursive formula. But can you give an explicit formula for the n term? Like let's say I give you 1. Can you produce me 1? 2 produce me 1. 3 produce me 2, and so on. Can you give a formula? Can you give? So the question is, can you give the explicit formula for n term? Let's call it Fn of Fibonacci sequence. Do you know how to do it? Is there an obvious way to do it or not? You come up with an explicit formula? You come up with an explicit formula? Or anyone see before the explicit formula? See before? Can you tell us? Quite ugly? Maybe a little bit ugly, but there's some beautifulness inside there. Anyone know or not? 1 over square root 5 times 1 plus square root 5 over 2 to the power n minus 1 minus square root 5 over 2 to the power n for n greater or equals to 1. What I said, there's a beautiful things inside here. There's something called golden ratio. So it's some linear combination of golden ratio inside there. So these are golden ratio. Okay. So, have anyone seen the assignment question yet? Already see it. So this is your first question. Group this. Okay. So if you see the assignment question, I said the deadline is Friday, next Friday. I think it's too rush, so it's extendable to the Monday. I guess to the Monday if you like. But I want, if you can challenge yourself, okay, do it before Friday. Okay. So do it before Friday means what? You only have one weekend, but do it on Monday, you have 2 weekends. Okay. Yeah. Okay, but if you need extend, tell me next week. I want you to try and do first, and you can come and get help during the office hour. Tuesday 2 to 4, and then Wednesday 3 to 5. Yeah, I already put the venue is A4113. So take note of the venue because maybe we will book a different room. Okay. So inside there, you can not just ask me, you have a senior there as well. You can ask them also. Be a lot of help for you. Okay, so you actually will see that the assignment is harder, okay, harder than your tutorial question, the question inside the textbook, because I give you time that you can do research. So please don't do it like one day. I got student like, oh, I tried others lecture assignment only 1 hour, try yours 3 hours. Of course not, I want you to study, you know. So don't do it at one. I mean, don't put it at the last. Don't put it do it at last minute. You know, think of the problem every day. Every day, don't need all the time think about it. Just maybe few minutes, maybe half an hour, 1 hour. Don't know. Come again tomorrow. Okay, no need like do it at one go. It's not like that one. I want you to think. I want you to go through the process of thinking. And you can do research, go and search. Okay? And then write in your own word. You understand it? Write in your own word. Okay? Don't understand? This is why office hour is there. Come and ask. Hey sir, I found this, I don't understand this line. Come and ask. Okay? So make sure you write in your own word. Reference. So if you collaborate, if Yu Liang collaborate with Isaac, so right now I collaborated with Isaac for this question. Otherwise, if I found that 2 of you has an identical answer, then you will get plagiarism. Okay, so there will be there will be a punishment. So if you submitted late, so the penalty is 3% one day. Okay, 3% of your full marks. Okay, one day. Okay, so if you need extra extension, well, today I sick out, let me know. Okay, is it clear on assignment stuff? How to do? Is it clear? Any question? No question? Okay, clear on how to submit, how to arrange your time. Okay. Okay. So tutorial question, you have to try and do. If you think that you don't understand the lecture much, you need to do exercises. Okay, tutorial exercises, and tutorial exercises come with solution. Okay. So after you do, what do you do? Rarely I have time to discuss tutorial question here because we have a lot of example in the lecture already. So one thing you can do is you can message me. So this question I do already, I don't understand. Even I look at the tutorial solution, I still don't understand. Okay, you can ask me. Or then go to your team chat. Ask your friend, hey, do you guys know how to do this? This one I don't understand. Okay, if cannot, then come to me. Does it make sense? Okay or not? So tutorial exercises you must try and do. Okay, you must try and do. Okay. So do to a stage that you think that I'm okay, I'm no. Then you can continue. If you don't know, then keep doing it. Okay. You know how I do tutorial question? For linear algebra course, when I study, I do the whole exercises inside the book. Not just the odd or even one. I do both. Typically, textbook only give you odd solution only. Okay, even solution they don't give you. Why? Because odd and even actually are the same type. Okay, or use the same method to solve. If the question look very different, they use same method to solve. So they all actually omit the even solution. Okay, so maybe if you try the even solution, wow, still cannot. Although I know how to do odd, even still cannot. What do you do? Ask them. Okay, you can ask me or ask inside your within your classmate. Okay, inside the team chat. Okay, don't be shy to get help. Get help is not saying that you are weak. It's not like that. We help each other. Okay or not? Yeah. It's not that you are weak. We are all learning. Okay. It's okay one. Just ask. Stupid question, ask only. Okay. Yeah. Okay, good. So we have introduced sequence. So next object. Okay, next object, let's motivate a bit. So next object is since we know the pattern now, okay, what we want to know is we want to know about far numbers inside the sequence. Okay. Okay. Now I give you a sequence. Can you quickly generate in your mind a formula for it? Can you quickly generate a formula for it? Huh? Want to try? 1 over n. Okay, good. Okay. So we want to guess. Hey, what is the far number? Very far number inside the sequence. What sort of number can appear? What sort of number can appear? I try. There's a lot, infinitely many. So you give me one. Hey, how do you know I like 1 million? Good, good. You say you want to be finance, right? Okay, good. No wonder you like 1 million. Next one. What do you think? What number can appear?
1 million.
1 million one, good. Okay, next one. 1 over 9 also can, yeah. 1 over 2 million, good. Very far already. 3 million, like? Wow, 5 million. Okay, we get very far now. So what can you see from these numbers? When we go further, these numbers are very close to 0. Okay, we will say that this sequence converges to, approaching 0. Okay, can we say it is approaching to -1 or not? Why? Oh, mathematics is not like this. 我讲不是就不是，不是的，你要解释给人家听为什么不是，对吗？对吧？对，为什么不是？为什么不是？For example, approach. Did you guys learn the idea of limit or not? In calculus 1, right? Okay. So why I can't say approach -1? If approaching -1, what number should you take at least? Yeah, you need to go to negative first. Are you going to negative anywhere? No one. How to approach -1? There will always be a gap. What gap is that? How big is that gap? And how big is that gap from -1 to the sequence of number? 1, at least 1. Cannot approach one. I'm always distant one with you. How do I approach you? Correct or not? Okay. So how about the others? How about the other example? Let's say we pick the constant sequence one. 0.999. Right, just now we had this example. So what's this sequence approaching? So when we write down sequence, always we write dot dot dot. Otherwise, we stop already. Yeah, actually it's continuing. So approach where? What do you think? Itself. Okay, so for constant function is very easy. Converge to itself. So So this motivate the definition of limit. So let's do the definition of limit. So a sequence an is said to have a limit L in R or converge to L. Okay, so both refer to the same thing. When I say converge to some number, meaning it has a limit. So how do we write this? So we write as limit n to infinity of an equals to L. The limit of an is equal to L. So what sort of limit? You take n to infinity. So every symbol here, there's a meaning. So make sure you know. If what? This is the most important thing coming after the definition. If the values of an get arbitrarily close to L when n is partial. Okay, so what is arbitrarily close? Arbitrarily close is 任意的，任意的 is arbitrarily close. What is this? Scribble. Scribble. But arbitrarily close. 我是任意啊。Trust it. As close as you like. As close as you like. As close as you like. I give you an example. So just now we claim that 1 over n approaches 0. Can we get as close as we like or not to 0? How close can we get? Let's say distant 2 from 0. How many terms are distant 2 from 0? At least, not at least, less than distant 2 from 0. How many terms? And from a 1 over n here is less than distant 2 from 0. How many terms? All of them. All of them, right? How about distant less than 1 from 0 then? So 1 is 1 and 1 less than. Less than 1 no? 1 minus 0 is 1 1 equal 1 1 is not less than 1. So accept the first term. Okay, no? If 0.5 close to 0 then accept the first two. And then you can go closer and closer. No matter how close you can get to 0, you always can find some terms inside the sequence as close as that distance. Does it make sense? As close or less than. So this what? So this motivate this picture here, or actually motivate this. Let me write down. Motivate this definition here. So more precisely, we will write lim of n to infinity of an equals to L if for every positive number epsilon greater than 0, there exists some capital N based on this epsilon, such that if we look for all the term behind this capital N, we know that an take away our limit is less than epsilon. Okay, can you imagine or not? Can you imagine this definition here? Okay, so what? So should I give you an example? So schematically, so how do we see this schematically? So last time I told you that an is a function, right? So we can sketch this function actually. Okay, so we can try and sketch this function. I also draw the R2 out, but really we just look at the domain of natural number. Okay. And then let's say, for example, our limit is this line here. Okay, this is the limit. So if I want to say that AN approach this line, what does it mean? So you can see that for n large enough, okay, it is arbitrarily close to L. Okay. Yeah, no. Maybe previous few finite term is quite far, it's fine. As long as the tail converge. Okay, we call it tail, the far behind term. First few term is fine. Because what we care is when S is large enough. So meaning very large enough. Okay. But don't worry. We won't study this in our course. Okay, we don't have epsilon delta in our course. But if you want to do project, you want to prove some proposition, then you need to introduce this epsilon delta. Does it make sense? Okay, so in our course, we won't do epsilon delta formalism, and you won't see proof like that. I won't assess those kind of things in this course. Okay, just make sure you know how to compute limit, how to see limit. Okay, I'll show you how to do it. So about this approaching arbitrarily close thing, right? I still want to give you an idea. So let's make a remark here. Let me ask you, does arbitrarily close to L meaning there's infinitely many terms equal to L or not? Do you understand my question? So one is arbitrarily close to L. The other is infinitely many terms equals to L. When n large, if you like. Do they equal or not? Why not? Okay, don't equals is different, but could one of them imply the other? Can one of them imply the other or not? Huh? No? Okay, why? Try. Consider a function, continue. E to the power x. Okay, so what happened to e to the power x? Continue. When you take x go to negative infinity, okay. Okay. Does everyone get what he said? So basically, if you set ex equals 0, what do you get? S equal to non-zero, but non-zero is not defined. Okay. So yeah. So what do I want to say here? So maybe reduce this condition a bit. Infinite terms equals to L for all large n. Okay. So if you have infinitely many terms equals to L for all large n, meaning what? Your tail is look like a constant sequence already. So definitely constant sequence conversion. But arbitrary close is different. You might not equal for some of the term, but it's arbitrarily close. Okay. So for example, the example I gave in so my example, the difference between my example to this example is my example look like this. I go the other way. Correct or not? 1 over n. Okay, so 1 over n is up. I said that it's arbitrarily close to 0, but the sequence never take out the value 0. Right? Why? There's nothing like 1 over 0, right? Undefined also. Okay, so there's no value for you to take out 0, but it is arbitrarily close to 0. So this is the power of limit. Okay, although you cannot approach 0, but the limit, although it cannot take out the value 0, but it can approach 0. But the limit of the sequence is 0. Does it make sense or not? Okay, so this concept you need to understand about this limit. You might not take out the value of your limit, but your limit is that value. Yeah. Okay. So this is a very important concept for you. Any question? Any question? Okay, because people tend to confuse. Yeah, there's no 0 here. Why the limit is 0? I never take 0 inside my sequence. Why the limit is 0? Okay, so you need to understand what is the idea of a limit. Okay, you get arbitrarily close. Okay, arbitrarily close. Okay. Okay, arbitrarily close and equal to L is different. All right, good. So typically in MA1, when we want to prove some limit is L, what we need to do? We need to prove this segment, because this is a definition, man. This true, only this true. Okay, so you want to prove this kind of segment, what do you need to do? You have a universal quantifier. Right? So you need to show for every epsilon, peak and arbitrary epsilon. Then existential quantifier, meaning what? For every epsilon, you need to find me an epsilon. Such that what? You need to verify this sentence here. Again, for all arbitrary n greater than equal to capital N you pick, so that this segment is true. With computation, we need to compute. For example, just now we pick an equals to 1 over n. So when you compute 1 over n minus 0 is less than epsilon. You need to prove that why there exists such kind of n epsilon. It is not trivial. This is not trivial proof. Okay, that segment actually is called an Archimedean property of real number. So if you are interested in doing that, you can do it in your project. Okay. Prove Archimedean property. So it's quite non-trivial. So that's why we get rid of this. So we won't do epsilon delta. So since definition 都不能用了，好像你把我双手双脚都切掉，怎么办？ Okay, so I need to give you new hand and new leg. Okay, so here is the tool I introduced to you. So here's the tool. So let's start with the first theorem we had in our class. So if limit of x to infinity, fx equals to L, okay, such that this L is in R, and x is in R, so our function is from R to R, then limit of n to infinity, fn equals to L for n in. Okay, so when you see a theorem, what is the main part you see? What's the main part you see? You remember, theorem is do you job, 你做功能. So you should ask, 它可以给我什么? What this theorem can give me. So what do you have to see is, so this structure is what? If you learn logic, this structure is if P then Q. So this theorem will give you Q. If something happens, you have Q. Okay, so this theorem is telling you that limit of Fn equals to M. So what does this mean? I just introduced this notation for you a minute ago. What is limit of n to infinity Fn equals to M when n is in n? Any idea? Okay, so yeah. And then Fn approaches L. So Fn get arbitrarily close to L when n large. Okay, so this is what? Sequence of limit of a sequence of. But how to if I want to say that this limit of sequence is L, how to prove it? If what? If I know the P. Okay, if I know the P, but what is P here? What's the P here? What's P here? Anyone tell me what's P here? A very obvious thing. I'm really asking obvious things, so don't be scared. What's P? Oh, limit of the continuous function. And but there's no continuous function here, right? Just a function. Limit of fx is equals to L. So what's the difference? Both of them are limit of fx equal to L. What's the difference between these two statements here? Sorry? Yeah, the domain is different, right? So first one is taking R as a domain. Second, taking natural number only. So taking natural number is what we define as sequence. But the P should be familiar to you, right? This is what you did for the whole semester in calculus 1, right? Compute limit of a function. So meaning what? So meaning, if you want to compute the limit of sequence, you can go back and compute the limit of the function defined by the sequence. Okay. How does this work? Let me give you an example. Give you an example first. So how can you view a sequence? How can you view a sequence as a function? So let's say we start with our favorite 1 over n again. So we have 1, 2, 3, 4, so on, right? Okay. So maybe make constant distance here. So we get 1 here, half here, 1/3 here, and so on. Okay. So this is sequence. But how do you view this as a function? Okay, so let me be precise here. This x is in R, this n is in n. How do you make it a function? So you fill in the gap here. Okay, so schematically is like you are joining all the point together. Correct or not? Why you are joining the point together? Because we know that natural number is also a subset of R. So you will meet natural number also. Okay, what you have in the sequence, you also have in your function, real value function. Okay, but limit of real value function is what you learn in calculus 1. You know how to compute. Did you guys use epsilon delta or just a normal high school method in calculus 1? What did you do last semester? Did you use epsilon delta or not? Yes, you used. Okay, yeah. This semester you no need to show that. Just assume you know. Okay, assume you know how to compute. Okay, limit for real value function. Okay, for MA1 we will use epsilon delta. But here no need. Okay, assume you know. You can even use high school stuff also can. Okay, so yeah, so this is how you get from a sequence to a real value function. Okay, so meaning if you want to find a limit for sequence, you can use calculus 1 knowledge to find the corresponding limit for the real value function. Okay, so for this proof, we won't prove, so leave it for MA1, or you can do it in your project. Okay, you can try and prove this in your project. So let's see how we use this. Okay, let's see how we use this statement here. So let's do a little bit different example here. So find the limit of 1 over square root. Let's find this limit here. So when this question appears to you, what's the first thing you do? What's the first thing you do? Okay, intuitively, you should understand your sequence first. Naturally, you need to understand your sequence first. 认识那个 sequence 先。How to understand it? How to understand your sequence? Hey, what's the definition of your sequence? Again, second, I will ask you again. What's the definition of sequence? List of number. But I only give you a formula. So you need to get a list of number out of it. So what's the list of number you get from this formula? What's the sequence? List of number. 1, power square 2, and so on, right? See, you see, we are using, step-by-step knowledge. Just now, at first, I asked you to find first, second, third term, right? You have to use it here. Okay, you have to use it here. So, if you, by observation, observe what is the limit here. By observation, you guess? Maybe 0. Okay, I want to guess it is 0. But how do you show it is 0? And maybe 0. Let's plot it up. So the maths I do, I like geometry. So when I do things, I like algebra and geometry together. So I will sketch this graph together. Out. So 1, 2, 3, 4. Okay. So here is let's say what? AN. Let's do. Let's put Y. So we have A1 here, A2, and let's say maybe here 1 plus square root 2, and then A3 lower a bit. Okay. So when I sketch this graph, actually I assume you know that what number is larger than what number. If you cannot figure out, maybe you take your calculator. So you can use some tools. For example, if you think that 1 over square root 2 is greater than 1 over square root 3, maybe you can try and move it around and then see that you actually get the right thing. Okay, so this is a very classical way to see. But anyway, so you see that this sequence here decreases. Okay, maybe it decreased to 0. Okay, obviously you observe that it cannot take out 0, right? Because there's nothing 1 over it, you can get 0. Okay, undefined. Now, how do you prove it? How do you prove it? I say you don't need to use epsilon delta. So what can you use? Yes, I only give you one hand, so you can only use that hand now. Okay, so that is the theorem. So what's that theorem? So that theorem amounts to make the sequence into a real value function. Okay, so you need to ask yourself, do you know what's the limit of? Let's look at the function 1 over square root x, the real value function 1 over square root x defined on R. Okay, so consider this. So what's the limit of x to infinity of 1 over square root x? Okay, so we know that this is equal to 0 from this one. Okay, you can use epsilon delta or what to show it. So you can use using epsilon delta. Otherwise, I just assume you know from calculus 1. Okay, then what? Then by theorem above. So by theorem above, we know that the limit of the sequence 1 over square root n equals 0, since the real value function counterpart has limit equals to 0 as well. Does it make sense? So we turn a limit of a sequence problem to a limit of a real value function. Okay, which you know how to compute from calculus. Does it make sense? Okay. So if you want to show a limit of a sequence, see if you can turn it to a question in calculus 1 or not. Okay. Okay. Any question about using this theorem here? So this is the first hand I give you. There are more hand I'm gonna give you. So this is the first hand I give you. Okay, without, so we can escape the epsilon delta definition. Okay, question? Question? Any question? Question, please. Seems like I got see some confusing things, but the question not changing. No? Okay. Does that make sense? Okay. 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 Then let's continue. So next example before we go into the next two. So yeah, I talked about convergence, right? I haven't really talked about divergent yet. What is the definition? What is divergent? So we define convergent. Okay, so how about divergent? Let's see about divergent. So if the sequence you cannot find any L such that the sequence converge, we will say that the sequence diverge. Okay, if you cannot find any L. Okay, if you cannot find any L. So meaning what? Meaning actually there's an extra quantifier here. There exists an L such that for all epsilon greater than 0, and there is this capital N such that AN is close to L for large enough N. Okay, so there's extra condition here. That L have to exist first. Okay, need to be existing first. If you cannot find such L, we will say that AN diverges. Can you imagine a few conditions that AN can diverge? Can you imagine? What can happen if AN diverges? If it doesn't converge to any L, what can happen? Obviously, if you take negation of convergence, that means the L doesn't exist, no? The limit doesn't exist. What else? The other cases is the sequence could diverge to, or let's not use diverge again. So approach to infinity or negative infinity. Okay, because we don't include infinity and negative infinity as our real number. Okay, it maybe get very close to infinity or very close also, arbitrarily close also. But the problem is infinity is not a real number. Okay, so yeah, sorry. What do you mean by answer? Example.
It's necessary. Can you approach it?
Oh, not necessarily. I mean, if it diverges, it could be that you cannot find the limit, or the limit is infinity or negative infinity. Because the L we consider is only in real number. Did I put that down? Okay, I did put that down. Yeah, R is in L is in R, so infinity is not an element of R. Okay. Yeah. Does it make sense? Okay. Yeah. Yeah. For example, right, if you take this section here, you can see that it approaches to infinity. Okay, but we don't consider infinity as our limit. Okay. There might be cases, we want infinity as our real number. That's what called the extended real number system. Okay, if you want to do research on it, also can. Extended real number system. You include infinity inside your space. Okay. This is actually very interesting space. If we go higher level max, you can imagine if we have a real line, right? So both sides is going to infinity. But once I add this infinity, somehow this line join together. Once this line join together, what do you get? Circle. Okay, so you will get circle. Okay, this is what we call a compactification of a real number. Compactify the real number. We add in a infinity. So, very interesting maths actually. Okay. Yeah, so this is topology. Yeah, continue. So let's continue with this example. So let's look at this one. So does the sequence minus 1 to the n converge? So this alternating, does it converge or not? Okay, if yes, to what number? Okay, I give you 1 minute. See how do you approach this question. I give you 1 minute to think about. You can talk with your neighbors. Okay, so what do you think? Does it converge or not? No, no, not converge. Why? Why? Huh? Not converge, only one reason, no? By definition, how can it be not converge? There doesn't exist an L such that the sequence can get arbitrarily close to L when n large. Negation, no? Okay, then you need to show this, no? So how to show this? So what do I tell you? When you get a sequence, what can you do? You plot the sequence out. Okay, plot the sequence out. So whenever you see the sequence, you can plot it out. Write down the terms and then plot it out. Okay, but I think the terms is quite easy to see in this case, right? So what are the terms you get in this sequence? What's the first term, second term, third term? Negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. Alternating negative 1. Okay. So since the sequence alternate between -1 and 1, it doesn't converge because we cannot find an L that can be made arbitrarily close, okay, for all n. So since it alternates between -1 and 1, it doesn't converge. So we cannot find a number L made arbitrarily close to all what? To all an, or basically I'm like repeating the definition of convergence. I'm just taking the negation, right? Okay. So the sequence diverge. But I'm not happy I'm not happy. 你讲不能找又不能找咩？你要证明给我看做不能找。Okay, so how to prove you cannot find one? So this is where the contradiction come very useful. Sometimes contradiction not useful one. Even if you prove a statement, you haven't tell me how to do it. You just contradict it. But this time contradiction is very useful. 要证明不能做的东西，假设你可以做。Suppose I have an L, it can converge. Correct? Let's say I say L equals to, let's say 1. L equals to 1. Okay? Let's say L equals to 1. Can I say that this sequence converges to L equals to 1? Can or not? So to answer this, you need to go back to the definition of convergence. Can you make arbitrary close to L or n large? Can or not? Got not? Got very large n, I have an equals to 1. So is it true? I can make the sequence arbitrarily close to 1 when n large? Can or not? Go on. A1, let's say 1 million is 1. 2 million also 1. 3 million also 1. Can I say deduce that 1 is my limit or not? Why not? Why not? Why not? Only? Don't think so. I think that one you try to use the theorem, is it? But that theorem just says that if the real value, if I know the real value function limit, and then I know the limit of the sequence, the limit of the sequence, but it doesn't say that if I don't know, yeah. Maybe you can prove that statement. You don't want, that's your project title. Prove that if a real value sequence diverges, then the limit of the sequence, corresponding sequence diverges also. Can prove it? Try and prove it. You think true? Prove it. Alright. Then if not true, then you come up with counter example. Also good. Then I give to next year exam. Okay, just kidding. Okay. Yeah. So can I deduce or not? L equals to 1. Limit is 1. Yes or not? 1 million is 1. A 2 million also 1. Or so far already. And very large. Can I deduce or not? Won't make sense or why? Instinct say no. So why is it no? The answer is no. So why? What? Think about 1 million and 1. What's that? Really what? 2 million and 1? Oh, negative 1. So, no matter how far you go, there will always be a term of sequence which is distant 2 from 1. You cannot make arbitrarily close already because it must be word for n large enough, O(n) large enough. Okay. Does it make sense? So similarly, if you pick different L, maybe L equal to 0, L equal to -1, then you can use the similar argument to say that it cannot converge. So we have proof for OL. OL cannot work. So this is what we mean by we cannot. Okay, cannot find, you just say 不能找就不能找了。就是说你去找了，找不到。Understand? Understand 了 ？OK， 所以不是说不能做就不能做了，是你做了就真的是不能，才是不能做，明白吗？Understand 了 ？Understand 了 concept? OK 啊 ？OK， so something like this cannot do, try and use a contradiction, okay, to prove it. What else I want to say here? But there's one observation here. I think you all also see it. Can we say that this sequence has two limits? Can you see that there's like one subset of number is stay at one? I mean you have two constant sequence, two constant subsequence inside here. Okay. So actually we cannot say there's two limit, so there's a violation. Okay, haram. Okay, you cannot do it. But we have a concept called lim if and lim sup, so superior limit and infimum limit. But we won't approach in this course. We'll do it in future. Okay, in MA1. So you can see that, for example, we will say that, lim if is -1. The limit of the infimum is -1. If the limit of the supremum is 1. So they are different. So if they are different, then this sequence have no limit. If lim if and lim sup is equal, then you have a limit. It is the same number. So this is what you will learn afterwards. Okay. So now you just learn that there's no limit here. And why there's no limit? We have another system to tell you. So this is max one, max everything very precise. And why no? Why no? Okay. What time is it? Okay, I think. Any question before we take a break again? Any question? If no question, let's break until 11:07.
数列的下表可以是复数的。
列的下表什么意思？
means the index of the sequence.
Cannot it natural number. Natural number.
前面这个
这个其实是不能，只是就一个靠近的概念吧。OK， 等一下我再clarify 一下。等一下我把这个画出来。OK， 等一下我 clarify 一下，颜色不可以复数，但是我只是想带出一个靠近的概念。等一下我解释。
If this one converges, there's this one.
Wait, later I show you. Okay, so let's start. So Jim Hong just now asked, there's a concern here. If we look at the fx equal to x here, if we look at the main extension number, it seems diverge, right? But what we are focusing is the negative part, right? But so he asked whether we can take can sequence had negative integers or not. Okay. So to solve this problem is very easy. You just consider e to the minus x. But why I put this example up? Because I want to discuss about arbitrarily close to R, L, and infinitely many terms equal to L. I want to discuss this condition. Okay. Maybe it's not in the right sequence setting, but it's similar in the sequence setting. So meaning, if I want to convert this to a real sequence example, I just consider e to the minus x. So I just swap the convergence, to 0 on the other side. Okay, e to the minus x. Okay, now that's why I pick 1 over n log, because that 1 over n leave from that side. Okay, so about this arbitrary close to L, although limit is 0, this is a bit like human relationship, right? Although we are very close, our limit is 0. But always there's some distance there. Still not the same. I'm still not you. You are still not me. Okay, although our distance, our limit is 0. Does it make sense? Okay. Okay. All right. Good. Actually, at Jiantuan, your max viewpoint is quite mature. Are you in the same batch with them? How are you? 19. How are the rest? What's the rest? Huh? What? You uncle? What uncle? How about the others? How about you? Oh, you 20. Okay. Others also 19, 20 like that, around that. Okay. I think yours viewpoint is quite mature. Okay. My supervisor once said, my PhD supervisor, sometimes it's not maths is too hard, or it's not that it's not that maths is too hard. It's just that you are not mature enough to understand it. I feel that is quite true. Because when I first learned epsilon delta in first year, I cannot get it. I simply cannot get it. No matter how you tell me. It's very hard for me to understand. After 2 years, in my third year, I work on the street, work on the path. Suddenly I understand it. Click. Oh, epsilon delta is like that. Oh, just click. They call it a eureka moment. You know what's a eureka moment? Suddenly you know something. Okay, it's not mature enough. So how to get mature? You need to experience your life more. Okay, talk more with others. Then in that way you can get mature faster. Okay, if you just stay on your little world, then it's very hard. Okay, it's very hard. You can, but take times. Yeah, it takes times. Okay. So yeah, so let's get second two of the days. Okay, we learn second two now. So this is the property of limits of sequences. Okay, let's get the second two of the day. So these two are only restricted with convergent sequence. Okay, you start with two convergent sequence first. You already know it converge. Okay, two of them. Okay. And we have a constant come into play here. So this constant here, it can live in R, real number, any R. Then what? Then limit of a constant is constant. What this means? What does this mean? So meaning you need to make this constant number into a constant sequence, because just now I tell you that we put sequence inside the limit. So this has to be a constant sequence instead. But on the right left, what C is this? This is a constant number. So there's a subtlety here, although I put CC on both sides. Understand or not? You understand? So the left-hand side C represent C, 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 infinitely many C. Okay, constant sequence. But on the right-hand side is what? C. Number only, a number. Does it make sense? Okay, so you need to understand what we can put after this limit operation. Okay, I call it operation. Later I'll tell you why. Okay, so you can only put sequence inside there or put a function inside there. Okay, so how to think about constant number as a sequence? Constant sequence? How to think of a constant number as a function? Constant function? Okay, do you know constant function or not? Fx equal to C for all x. Constant function. Okay, constant sequence, an equals to C for all n. Okay, what else we can do? Okay, we can multiply. Okay, multiply constant to a sequence. Okay, and then ask what's this limit? I know an converge already. So how about C times an? Does it still converge or not? What do you think? You guess. Guess first. Use your intuition. Train your intuition. Does CAN converge or not? CAN is what kind of sequence? I asked you sequence in third hour already. So what's the definition of sequence? List of number. Okay, in a definite order. So CAN, what's this list of number you have? What's the number you get from CAN? Yeah, CA1, CA2, CA3, CA4, CA5, CA6, CA7. So what's the difference with AN? This sequence. Every term multiplied by C. Okay. So if AN converges, CAN converge or not? What do you think? Yes or no? Two choices. Yes. Okay. If yes, you need to tell me, if it converges, must converge to one L. So what's that L? Yes. It's simply C times the limit of AN. It seems like I can just pull the C out. Okay. Okay. Then what else? I can add two convergent sequence together, add or subtract. Okay. I mean, subtract is just addition of a negative bn. Okay, so both of them are addition. So what's this limit? You want to guess? You guess what's this limit here? Does it converge? First of all, converge. So if converge to what? Want to guess? Right? I guess. Limit an plus minus limit bn. Yeah, we can split. And you need to make this very intuitive. In the exam, let me tell you first. Let me give you a trailer first. In the exam, I will allow you to bring a cheat sheet. Okay, you can copy all the formula example if you like to the midterm. Midterm, I'm talking about tests. So make sure you know how to use all these theorem. Let it make sense to you, not just memorizing. Okay, so you can use it easily. Okay, so now I'm trying to teach you how to appreciate or how to motivate this proposition here. Okay, what else I can do with two sequence? I add already, I scalar multiply already. What else can you do? Linear algebra, what can you do? You add, you scalar multiply, and then what can you do to matrix? Multiply together. So I also can consider like the sequence A1, B1, A2, B2, A3, B3, A4, B4, A5, B5. Okay? Does it converge or not? I put them together, seems like they have to converge, right? But converge to what? Yes. Huh? I can split sum, I can split scalar multiple, so I can also split the multiplication. So it will converge to limit of am times the limit of bn. Okay, if maybe I put a bracket is better. Okay, so you can see here, all of this equal sign is equal as what? Number. Okay, so you can see that this limit here should be a number L in real number. And then the other side is an addition of number or multiplication of number. Okay, so both sides have to be number. But beside limit is what? Sequence. The limit of a sequence give you output you a number. So if you have a limit, input a sequence, it will give you a number. Okay, either you have a L, either L doesn't exist. Yeah. Okay, so last thing. So this is very special. So you can take the quotient, okay, an by bn. Okay, so do you want to guess? No need to guess. Can you predict? What come next? Limit an over limit bn. But now there's a difference. I mean, there's a denominator here. So you need to make sure that your denominator cannot be 0. Okay. So again, to prove this is actually non-trivial. We won't prove it. Okay, if you want to prove it, you can do it, all this using epsilon delta. Okay, so here is a proof epsilon delta. Yeah. Okay. Okay, you can prove it. Okay, otherwise we just use it. Okay, we just use it. So what can you see here? Is it split sum? We split the scalar multiple. What is this? Linear algebra. Split sum. T what is the notation used? Tx plus y equals to tx plus ty. Tcx equals to c times tx. Remember, linear transformation. So it specifies these two properties here. So this is a linear transformation from where to where? from the space of convergent sequence to real number. Okay or not? So, I mean, if we talk about linear transformation, we need to show that it is a vector space on both sides. Okay, real number is easily a vector space, but you need to show that convergent sequence form a vector space. How to prove it? An axiom, huh? Okay, go do it. An axiom, huh? Check that the space of convergent sequence is a vector space. Okay, so I want to put a remark here so that you can easily talk about all these property here. So remark, this lim n to infinity is a linear operator. Okay, operator or transformation, we can swap and use their equivalents of the space of convergent sequence. So you need to check convergent sequence from a vector space. Okay. So you need to find how to add them, how to scalar multiply. I already tell you, just multiply every term. How to add term by term. No? Then what is the identity there? The additive identity. What's the sequence that you add to all sequence, you get back the original sequence? The zero constant sequence. Correct. And then what's the inverse? Go and do it. Okay. But this one is extra. It's not important for our course. I just want to give you an idea. Okay. How to talk about these things. Because you see, if I say that, oh, lim n is a linear operator on the space of convergent sequence, what does it mean? 2 and 3 already drop for you. Okay, already imply 2 and 3. Then others one is extra. Okay. All right. Let's see how we're gonna use this property to find limit. Let's do example. Okay, I'll let you try. Let you try. So find the limit of n to infinity of 3n squared over 7n squared. Okay, I'll give you 3 minutes. Try and find this. So I give you 2 hands now. Okay, you got 2 hands to use now. Okay, 2 theorem to use. All right, see which hand can be utilized here. Let's try and do this. You can discuss and you can make noise now. Yeah. Okay, let's start. Let's give me final answer first. Okay, what's the final answer you get? What answer you get? Does it converge? Converge to where? 3/7. Yes, it is 3/7. So let's see how we prove it. Can you share with us how to do it? How you do it? Okay, before that, let me list down. So the first thing first, what do we do? If this sequence is easy to find the limit, we don't need to use all the hand thing, right? So let's list down the term. So what is this sequence here? So, 3/8, 12/29, 27/64, 48/113. Okay. For me, I can't see this 3/7. Okay. Maybe Ramanujan can. I cannot. Okay. So how to prove this? How to get this? First theorem. Okay. So how do you start? So what do you start? So you consider the real value function counterpart, is it? Okay. So we replace this. So typically, when we look at the real value function counterpart, we replace n by x to denote that we now consider the domain real value function, because you always use x, right, for real value. Okay, and then we use n for natural number. Okay, so this is the just convention, but as long as you know what you are doing, that's fine. So how do you compute this limit here from calculus 1, is it? So how do you compute this? Good. So what can you do? You can divide by the highest power of x. So you get 1 x squared. And then okay, you can put limit into it because all of them are how to say, convergent function. Is it convergent function or not? Or the limit exists for all the functions inside. Okay, so there's so what I'm using is there's a similar proposition for a function that has limit. Okay, so you can bring the limit into it. So please check, please check why you can do this from calculus 1. Please check. Go and find. Okay, so this is a similar. So I will make a note here. Similar property, similar to the property of convergent sequence. Okay, and then limit of x to infinity of 7 plus limit of x infinity of 1 x squared. So let me test you again. When I put this 3 here, 7 here, what does this mean? Does it really mean 3 and 7 or not? What does it mean? It must be a function. Okay, either function, either sequence. We only can find limit for sequence or function. But in this case here, it is a real value function. So what do we get? 3/7 plus 0. Okay. Right, good. So this is one way. Does anyone get different way to compute or not? Or everyone use the same way? What? Anyone has a different way to do it? Got or not? Right? Same way. Exactly the same. Any other different? Same way. Same. What? No variety like that. Okay. Right. So this is the first theorem, right? So this is by first theorem, by theorem before. Theorem before, you know that. Lim of n to infinity of 3n squared of the 7n squared. So you are using theorem before. I just taught you to use the property of convergent sequence. No one use it. 不是浪费了。好。Sure. I'm not blaming you. Don't worry. I'm not blaming you. I'm not blaming you. I was trying to motivate them to use different way. Not blaming you. No worries. Okay. Blaming you. So how to use the property that I introduced just now? Can we use the second method to solve it? It's okay to use the first method. Just that I want to introduce you how to use the second method. So to use the second method, you need to do what? You need to find convergent sequence. You have convergent sequence in this sequence or not? Reading the sequence. Can you split the sequence here into some convergent sequence or not? Things like not, right? Because if you look at 3n squared diverge, correct or not? Getting larger and larger. 7n squared also larger and larger. 没有路了咯，路关起来了咯，是吗？ No, this is not how you do the first way. You also turn it into something else. I also can turn it into something else, right? So not that. We can also, okay, do the same trick immediately on the sequence, not on function, real function. So we do it immediately on sequence. Okay. So what do we get? 3 over 7 plus 1 squared. Now what happened in this case here? A constant sequence 3 converge or not? Constant sequence 7 converge or not? Sequence of 1 over n squared converge or not? Converge to where? 0. So it's like a combination of convergent sequence, right? Okay, how to combine them? First, you add the two sequences in the denominator, and then you take the quotient. Okay. Okay, so we have 3 convergence sequence here. Okay, so what can we do here? So, first of all, we see that limit of n to infinity of 3 is 3. Okay, this is also by property, right? By property 1. Okay, and then limit of 7 is 7, also by property 1. Okay, limit of n equal to infinity over 1 over n squared is 0. How to prove this? Use what? Use your calculus 1. Okay, you need to pull it back to your function. So this limit equals to the limit of x to infinity of 1 over x squared. Okay. By the theorem and calculus 1 knowledge, okay, we know that 1 over n squared converges to 0. So you have three convergent sequence. So since constant sequence 3, 7, and 1 over n squared are convergent. Okay, are convergent. So what can we do? So we can use the property of sequence again. Okay, how do we use the property of sequence? Okay, how do we use it? So this one I put by theorem before and calculus 1. So by property of sequence, how do we compute the original sequence here? So limit of 3n squared over 7n squared plus 1 is equals to the limit of n equals to infinity of 3 over 7 plus 1 over n squared. Okay, which is what? I know these 3 pieces are convergent. So I can compute that this limit is equal to limit to n infinity of 3 over limit of n to infinity of 7 plus 1 over n squared. Can I write like this or not? When can I write like this? Still remember? When can I write like this? Say like this. If this number here is not 0. But do you know that this number is not 0 or not? Because we know that 1 over n squared converges to 0. And this one converges to 7. So if you add them together, they converge to 7. So I can write this. So after that, I can write this, and then this is what we have. Sorry. So the whole number is just 3 over 7 plus 0, which is 3 over 7. Yeah, no? Okay. Okay. I got another way. Let's do a third way. Okay, I don't want to divide 1 over n squared. Can I still compute it? The limit or not? Is there other way that you learn in your calculus 1 you can compute a limit? What? Yes. Good. You can use L'Hopital rule. So let's say we go back to the first way. We want to compute the limit of the real value function again. So fx equals to 3x squared over 7x squared. Okay. If you simply plug the limit, plug the infinity into this function here, what do you get? Infinity over infinity. Okay, so this is a condition that you can use L'Hopital rule. Anyone can recall what is L'Hopital rule? Anyone can recall? Anyone can recall? Limit of a quotient of function is equal to the limit of the first derivative of f divided by first derivative of gx if what? If both of them is 0 or both of them is infinity. Okay. I think I won't ask you to do this as your project one because this proof actually is very long. Even when we taught in MA1, we just sketch it. It's very long. It's tedious, I would say. Not hard, but tedious. Actually, there's more general version of this L'Hopital. One of them could be 0, one of them could be infinity. You also can use it. Yeah, there's more general version of this. Okay, I don't recommend doing this in your project one. This is quite long. Okay. But I recommend you go and look CC. You can look, study on your own. Okay, if you like, if you have time. If not, it's okay. You can use it. So how to use this? So since we know that it's limit of infinity to infinity over infinity, right? So what we can do? So by L'Hopital rule. So here, let's say by L'Hopital rule here, what can we replace with? We can replace by 6x over 14x. Okay. Still, we get infinity over infinity, right? So you can apply L'Hopital again. So what do we get? 6 over 14. But we know that limit of a constant function is just the constant. So which is 6 over 14. But what is 6 over 14? You can simplify it to get 3 over 7. Okay or not? Okay. So again, so this one is by finding the real value function counterpart first. Okay. So, and then you will get 3 over 7. Okay. So there are 3 ways I'm presenting for you here. Anyone got different way from these 3 ways? Feel free to show me. If you are shy, you send me. Okay. Okay, so what I want to show you is mathematics you can get to one answer with different way. Cannot have different answer, but can have different way of solution. Okay, answer only got one, but can have different way. Okay, so this is the beauty of maths. Yeah, no, does it make sense? Okay, in this case, let's skip the next two example. If you see in your in your handout, you will see a sequence of n over square root en plus 2, and also the other sequence ln n over n. Okay, so I leave these two as a homework. Okay, I will provide solution also. Okay. Try do it at home. Make sure that you know what you need to use, what you can use. Okay. Basically, I show it in one example already. Okay, check whether these sequences converges. So typically, when something that I left as homework is those method that I already gave you. Okay, so you need to try and see how to adapt it. Okay, it's the same way to solve usually for homework question. So try and see if you can apply what I teach or not. Okay, so this will see whether you understand what I say or not. Okay, if you can, then good. So before we end, I think we need to go further a bit. So let's go further a bit. So let's go to squeeze theorem. Squeeze theorem. So this is a squeeze theorem for sequence, not for function. Don't confuse. So this is a squeeze theorem for sequence. Okay. So squeeze theorem says that suppose that AN and CN converges. Okay, not just converges, they converge to the same number. Okay, same number. Let's call it L. And so there's a squeeze here, right? We want to squeeze something. So let's squeeze Bn. Okay, such that An is less than or equal to Bn, Bn is less than or equal to Cn for all n greater than equal to n. Hey, is everyone okay with this shorthand notation for all? Okay, everyone understand? You know why all for all right like this? Why? Don't why? Inverted A, right? Inverted A. You know why they invert the A? All. For all. Yeah. Okay, for all use A, right? So why invert the A? Because in old day, how they type using the typewriter. Okay, so if you use the same A, then there's no difference with the normal A. But what they do is they turn the button around and click. You know, a typewriter, click, 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 click. So they can turn the button, invert the button, and then tap. Yeah. Okay. Right. So squeeze. Then what? I haven't give you the result yet. Then. So this is a theorem, right? So you need to look for the result that this theorem can give. So this result here is, what's the Q here? So Q is this part. Okay, P is everything before it. So there are two P here actually. Okay, so maybe name it P and R. So it says that if what? If P and R happen, then Q. Okay, so it tells you about a limit of some sequence. But what this sequence is? This sequence is squeezed between two sequences. Between what kind of sequence? Between two sequences that converge to the same thing. Can you imagine the picture in your mind? Can you imagine? I said these mathematics, you can draw it, right? You can sketch it. You can do it geometrically. So can you imagine or not from these words what the picture should look like? What's the picture should look like? What can one draw? What can one draw? Yeah, try imagine now. Okay, what can one draw here? So you could start with a limit here. Okay. So AN squeeze from below, CN squeeze from above. You're going to stay above BN. Okay, one way you can see it is maybe you see it in this way. So let's say I gave a convergent sequence to L. So this is CN here. And convergent AN from the bottom. Say like this. Okay. Then where the BN should lies? The BN should take values in between AN and BN. Okay. So maybe it live in the middle. What color I haven't used? Use this one. So it lives in the middle, maybe. Okay. Maybe you can sometimes take value at AN and CN because I allowed them to be equal. Okay, but this at most you can do. You cannot go outside. Cannot. Okay, must be squeezed inside here. From this picture, is it clear that your BN should converge to L? Because it's like squeezed from both sides already. Okay, both sides is arbitrarily close to L already. You are in the middle guy. You must also be close to L. Okay. Does it make sense? Make sense or not? Why only this side no, this side no respondent? You guys understand what I said? Understand or not? If both sides, like the door, is arbitrarily close to L already, you are standing in the middle of the door, right? You should be also close to the middle. Get squished. So that's why this is called squeeze theorem. You get squeezed. Okay, squeeze. Okay, squeeze to the same place. Okay. Yeah. So this theorem we won't prove. You can do it in your project. Okay, we won't prove it. You can do it in your project. So I want to make a remark here. There's a very subtlety, subtle condition here. So this squeeze theorem doesn't imply the following. So what's the following? So if AN less than BN less than CN, okay, I purposely throw away the equal sign. Strictly less. Maybe you think like it's more squeeze or more squeeze, right? Okay, but it doesn't imply that the limit of BN strictly lies between the limit of AN and limit of BN. Oh, sorry, the limit of BN doesn't strictly lie in between the limit of AN. Can you think of an example? The key point here is the strictly. Strictly. Okay, so can you think of an example? Counter example to this one. Very easy counter example. So in my class, you need to learn how to think about counter example. Okay? Because in exam, I'll ask you to determine whether a question, a statement is true or false. If true, prove it. Is false, maybe you come up with a counter example. So think about this for a while. Can you come up with a counter example? So I give you the key. The key here is the strictly sign. So if you want to show that it's false, maybe you need to create some equality sign. Okay, so consider Bn equals 0. Cn equals to 1 over n, maybe, right? Making a sequence. Then An equals to negative 1 over n. So what do you expect here? So once we get this line right, you can start draw already. 0, 0, 0, 0, 0, 1 over n, 1 over n, 1 over n, negative 1 over n, negative 1 over n, like that. Okay, but in the end, what do you get here? What's the limit of all this? You know that these are convergent, right? Just now we discussed limit of constant sequence is what?
0. 0, right? Limit of constant sequence is just 0. And limit of 1 over n, we know that, right? 1 over x converge to where? 0. So by the theorem, we know that limit 1 over n is also 0. Okay. And then how about the other one? I think this one is C, huh? C have to go this side. Limit of minus 1 over n. You can consider this as using the property that this is equal to the what? Minus of the limit of 1 over n. Correct or not? But we know that limit of 1 over n converge, so this is minus 0, so 0. So you see, we're using everything what we learned just now, okay, to do something different now. Okay, we're using whatever we learned. Okay, but all of them are 0. So they should be equal. So they are not strictly less than. Okay or not? Yeah. So does everyone get the idea of counter example or not? So if you want to show that if P then Q is false, then you just assume P, prove not Q. Okay. Or not, maybe get not. Okay, to get the counter example. Okay or not? Is it okay or not? This must be okay. If not, you for sure don't know how to answer the question. Do you want to ask now? I can repeat the logic for you again. Anyone want me to repeat the logic? Logic. Repeat? No need. If you need, I can repeat. Never mind, even for one of you only. If okay, then okay. I'll be fine. You'll be fine also. Okay. All right. So yeah, Swiss theorem doesn't imply this thing. So maybe you would think that why this is more squeezy or strictly, but actually the different phenomenon can occur. Okay, let's do one exercise and then we finish. Or do one exercise we finish. So let's see how to use this. So find limit of sine cube n over n. Find this. So mathematics is like this. I teach you 1, 2, you use 1, 2. Okay, so you don't need to worry about I can use other stuff or not. So since I teach squeeze theorem now, let's see how to use squeeze theorem here. Okay, how do you apply squeeze theorem? Can I give you 1 more minute because we are short of time. Okay. Anyone get the limit? Or can you tell me how you squeeze first? Between 1 and 0. Is sine qx between 1 and 0 now? Negative 1 and 0, right? Because we know that sine x is in between 1 and negative 1. So if you take all the number inside there and then take cube, we should still live inside negative 1 and 1. So since we know that sine n is in between negative 1 and 1, we can see that cube of them is still living inside there. Actually, you can prove this also. MA1 first class is to prove this kind of property. But I think you assume this in your high school also, right? The number in between 0 and 1, 0 and -1. If you take power, it still live inside there. But you can prove it, okay, with proper tool. And then what else? But what you consider is sine cube n over n. Okay, so you can divide n or the sine, both sides. Okay, so it is squeezed by 1 over n. Is this squeezing useful or not? Is it useful? Is this squeezing useful or not? Why is it useful? To use squeeze theorem, what do you need to know? You need to start with what? Two convergent sequence. Not just converge, they have to converge to the same point. Okay. So in this case here, this two bound here, do they converge to the same point or not? Yes, so they converge to where? Converge to where? 0. Okay, we just computed just now. So you can see that if you look at their real counterpart, they converge to 0. By theorem before, we know that the sequence also converge to 0. Okay, so have we satisfied all the property of squeeze theorem that you need? Okay, you are squeezed by two sequence, and then the two sequence converge, and then they converge to the same number. So this means what? What does the squeeze theorem tells you? A squeeze theorem, the middle theorem will converge to where? To the same limit. Okay, which is in this case 0. Right. Can you draw this or not? Can you draw this? Can you draw this? Draw this. Okay. You can see that sine cube n is a sine n, but when n get large, right, it get divided by a larger number. So meaning the amplitude decrease. Okay, but it's still periodic. Okay, so you could expect something like this. Something like this. Okay, just a sketch. But what does it mean by squeeze by -1 over n and 1 over n? So where is -1 over n and 1 over n? Okay, so the real counterpart should be looking like this. This part should be 1 over x. But 1 over x got the other side, right? Where is the other side? At the bottom here. Okay, and then the other one is -1 over x and 1 over x. Okay, does it make sense? So this is how it gets squeezed by these two functions. Then across 0 positive side, one is above the other, and then less than 0 is the other way around. Okay. But what we care, where do we care? Where do we care? We just care about the positive side here. So this is what written here. Does it make sense? Okay. So if you look at the real function counterpart, you will see the whole picture. Okay, but if you see just the natural number, you just see one side. Okay. Yeah. So this is algebra. If you replace with different domain, you will see different picture. You can imagine I replace with complex number. Also can. Okay. But for us, we only stay to real numbers. Real numbers, natural numbers, that's all. Okay, if we replace with complex, then there's the second year, second sem, complex analysis. Okay. Right. Any question before we finish today class? Any question? Any question? If no question, we'll see you next week.